Bismillahirrahmanirrahim. This is the second topic of Geotechnical Engineering 2. So this topic actually deals with stress distribution in soils. So first of all, we'll talk about geostatic stresses. So geostatic stresses are also called as overburden stresses. These are actually stresses due to the self weight of the soil mass. That means it does not include any self weight. The weight only due to the load from the weight of the soil. So that is called as the geostatic stresses and overburden stresses. So for example, if I draw a ground surface here, so this is a ground surface, and let's say these are two layers here. So let's say the unit weight of this soil is 18 kilonewton per meter cube, and unit weight for this soil layer here is, let's say, 20 kilonewton per meter cube. So and also assume that the thickness of each layer is 10 meters. So the overburden stresses or the geostatic stresses at the bottom of the layer due to all the two layers, so I can simply calculate it by this formula, that sigma v is equal to 18 into 10 meters plus 20 into 10, or the simple formula is gamma 1h1 plus gamma 2h2. So the answer that we get here in kilonewton per meter square will be the overburden stresses due to the self weight of soil. You see that there is no load coming from external loading, and by external loading I mean any house or any structure that is built on the top of the ground surface. This is only due to the self weight of the soil, and we have been doing this example previously when we were discussing the settlement analysis in our Geotech 1 course. Alright, so talking about the geostatic stresses, the stress that I just calculated is also called as a total stress, and we have already discussed in Geotech 1 that there are two types of stresses when load is transferred from the soil, from within the soil body. So those are the total stresses and effective stresses, and as well as we also have the pore water pressure. So in the same example, the value that we calculated, so this value calculated here is called as the total stress. This is called as, let's say, total stress. So this is 180 and this is 200, so this gives me a total of 380 kilonewton per meter square. So this is the total stress, and if I want to draw the diagram for the distribution of total stress, so how will I do that? Let me extend these lines further so I can have a plot for the stress distribution. So let's say I will first plot the stress distribution for the total stress. So this is total stress. So at the top of the, let's call this layer 1, and let's call this layer 2. So on the top of the layer 1, and I want to calculate total stress, so I know the formula is gamma 1 h1. So gamma 1 for the top layer is 18 kilonewton meter cube, and h1 is 0. So this will naturally give me a 0 value. And at the bottom of the first layer, the formula would be again gamma 1 into h1. Now this time, because we are 10 meters below the ground surface and the unit weight is 18 kilonewton per meter cube, so it will be 18 into 20. I'm sorry, 18 into 10. So that means it will be 180 here. So I will draw a straight line here, and this value is 180. And then I want to calculate the total stress at the bottom of the second layer. So I know that total stress at the bottom of the second layer is 180. We have already reached here, so that means 180 plus gamma 2 into h2, and gamma 2 into h2 was 180 plus, that was 20 into 10, so that gives me a total of 380. So my value at the bottom of the second layer is 380. So this figure here, this is called as the total stress distribution. So this is how the stress will be distributed through the soil mass. You know that it's a straight line. Why is it a straight line? Because we see that in the equation total stress is equal to gamma into h. This remains constant for a layer. This remains same throughout the layer. The only variation is h. So as the value of h increases, so does the value of stress increases. So it's a directly proportional relationship. So that's why we end up getting a straight line here. Okay. Now imagine that we have a water table at the end of the first layer. So I'll use this line here. So assume that this is the water table here. So for geotechnical purposes, for the subject purpose, we assume that below water table the soil is fully saturated, and above that soil is in its natural state. That means it can contain both water and air. But for our numerical purposes, for geotechnical engineering 1 and 2, we assume that the soil below the water table is all saturated. That means it contains only water as well as solids. So now we will calculate the pore water pressure for this figure here. So I'll draw a diagram here. I'll draw a straight line. Let me darken this up. Okay, let me thicken this up. So this line here, this is for U, that is pore water pressure. So at the and the formula for pore water pressure is gamma W into H. And remember that the H value, this will start from water table and it will increase downward. So that means there is no water table in the top of layer 1, so that means we'll get a value 0. And also remember that on the water table H is 0, so that's why always pore pressure value will be 0 on the top of the water table. So that means we have a 0 line throughout the layer 1. And when the layer 2 starts, so we know that at the start we have 0 because it's the top of the water table, and at the bottom I'll calculate that gamma W into H. I know that gamma W is 9.81 in kilonewton per meter cube, so multiply that with the 10, that is the thickness of the layer 2, so 98.1. This is the pore water pressure diagram for our case. This is the pore water pressure diagram. Okay, and lastly, we know that effective stress is equal to total stress minus pore water pressure. I'll come to that detail how does that happens, but for now subtract these two figures to get the effective stress diagram here. So this is effective stress. So we know that it is 0, 0 minus 0, 0 is here, 0 minus 0 is 0 again, and here it is 180 minus 0 because this is 180 and this is 0, so that means it remains the same, so 180. And here in the phase 2 it will be 380, that is the total stress at the end of the layer 2 minus 98.1, that is the total stress at the that is the pore water pressure at the bottom of the layer 2. So this gives me approximately, if it is 98, so that will give me maybe 280 something. Yes, 282 maybe, 282 approximately, but you can check that. I didn't calculate it, but this is by subtracting the total stress value minus effective stress. That will give me the effective stress diagram. So this tells me that at any point in the layer I want to find out what is the value of total stress, pore water pressure or effective stress. So I can simply use this diagram to find out the value of any component that I want. Now coming to the explanation here, that we were discussing that total stress is equal to the pore water pressure. So to explain that with the diagram, so let's imagine a soil element here. This is a small soil sample. Let me convert that. Okay, it is open. So we know that under water table, I'm specifically taking a sample from under the water table. So we know that we have solid particles that are in the voids here, and we know that because it is saturated and under water table, so that means that the space that is free, or that is the void space, is all filled with water. So the circles that I'm showing, this means that these are the solid particles, and the space, I'm not covering it properly, but you should understand it, that this void space is completely filled with water, and the circular portion is all soil. This is all soil. So I'm coloring it in brown color so that you have a clear idea that what do I mean by that. So yep, this is here. So okay, all right. So imagine that I'm applying a load. So let's say this is the maybe load application area, and this is load P. This is being applied on the soil specimen. Okay, so we know that load will be transferred. If you remember Terzaghi's one-dimensional consolidation theory, he says that load is transferred through the soil mass by two methods. First one, the load will transfer from grain to grain contact, that is called as the effective stress, and the second method is by increasing the pore water pressure. So that means this load P here, okay, it is being transferred from grain to grain contact like this. So if this is the load transfer phenomena, so this portion of load transfer, okay, this is going to some other particle here. So this red colored is the effective stress. So this is the, or you can say that as grain to grain contact. So this is load transfer by grain to grain contact. The second way in which load is being transferred, like the portion here that is directly on the voids here, so that results in increase in the pore water pressure. Okay, the pore water pressure inside the voids, it will increase, and it is indicated by U, that is the pore water pressure. Okay, so and if the total load that is being transferred, that is stress equal to P over area's area on which it is acting, so this will be equal to effective stress plus pore water pressure, and in other words, effective stress is equal to total stress minus pore water pressure. This we already saw that in the previous equations. Okay, so just to jog your memories, we studied in the Terzaghis one-dimensional consolidation theory that once we were if we imagine in the same figure, if we think that this hole is really closed and there is no way for water to escape and there is no chance for volume change, you can imagine that this is a steel box and this is the piston that is fixed. Okay, so once I'm applying all the load, so all the load will result in increase in pore water pressure. There will be no grain to grain contact load transfer in the soil specimen. So once we allow volume change, or once we allow water to move out by any way from any side, maybe we make the sides porous, so what will happen? The excess pore water pressure, which is by the way indicated by a delta U, that means increase in pore pressure, it starts to dissipate until it becomes zero, and as soon as it is dissipating, load is being transferred from pore pressure to the effective stress. So now we know that it's a vice versa process, and a time will reach when the maximum volume changes happen. Okay, at that time all the pore pressure, increase in pore pressure has become zero, and all the load would have been transferred from the grain to grain contact, and all the load will be effective stress. To understand this in a more proper way, let's do an example which we are already familiar with. These are small definitions. I'll hand out this whiteboard file to you guys so you can read it easily. So coming back to our example, so this is the apparatus for the direct shear test. We are already discussed that in our lab portion and also in our previous lecture. So we see that there is a failure plane. Let me highlight that for you. So we want to calculate the normal stress that is acting on the failure plane. So and also it is important to note here that we have in this case our soil specimen is submerged. So to highlight that, what will I do? I will submerge that with this blue color. So you see here this whole portion, so that means this whole container is filled with water. Okay, so this hole is filled with water. So if I want to calculate the pore water pressure at the failure plane, so I'll highlight that this is the red color is the failure plane that we are interested in. We want to find out the pressure on the top of it, normal pressure or the normal stress. So the pore pressure, we know the formula already, it will be gamma W into H, and H, as you can see it here, that it is from the top of the water table up to the failure plane, so this is H. So that is easy. So total stress, we know that it will be equal to the load per unit area, right? So if you remember from the example, we know that area of the direct shear box is 6 centimeter by 6 centimeter. Okay, and the load is that, so if we know the load, so the top load on top of it will be all this load here. That means the load of the porous stone, load of the upper half of the shear box, or load of the upper half of the sample also, and also it includes this ball which is used for the load transfer. Okay, and also the additional load that we are applying. So we can write it here that total stress is equal to W plus P over A, where W is the load, of the specimen, of the upper half of the porous stone, of the steel ball, and P is any additional load that we are applying during the test. Okay, so let's see. So let's say that in the start we do not apply any external load, that means P is equal to 0. Okay, in that case sigma should be equal to W over A, and it has been calculated in by the actual field experiments that the weight of the specimen as well as weight of the upper half of the porous stone as well as the upper half of the apparatus, that weighs equal to 12.4 newtons, and the area has been converted to meter squares, that is 0.0103. So this gives us a total stress of 1.2 kPas. So as you've already seen, the pore pressure, we call that as U naught. Why we are calling it U naught? Because we are not applying any external load, and this is the initial condition before starting any test. So that is simply equal to gamma W into H. So H is calculated to be 0.051, and H was the height of the Fourier plane from the water table, okay, or the depth of the Fourier plane from the water table. So that is U, and now we want to calculate effective stress, so that will be equal to total stress minus U, and we have already seen that total stress was 1.2 kPa and U naught was 0.5. So I can say that in initial condition sigma dash is equal to 0.7 kPa. If you want to put a knot here, so it will indicate that this is the initial condition. Also goes a note from here and also for here. Okay, now we come to the second case. We assume that we have applied an external vertical load of 200 newtons. So increase in porous, increase in the normal stress will be 200 over the area, that was 0.0103. So 19.4 is the delta sigma, or increase in the normal stress. So total stress at that stage after application of the 200 newtons load will be sigma naught plus delta sigma. It gives us 20.6 kPa. Now we know that from Terzaghis theory, and we just discussed it already, that if there is no volume change and there is no space for water to escape, so all the external load will result an increase in pore pressure. So based on that theory, delta U will be equal to 19.4 kPa. That happens to be the increase in stress that we have applied. Okay, so total U will be U naught plus delta U, so 0.5 plus 19.4 is 19.9, and lastly sigma dash is equal to sigma minus U, and total stress was 20.6, and and the pore water pressure is 19.9, giving us the effective stress of 0.7 kPa. So this is very important to note here, that in the first case, that was in the static case, when no load was applied, effective stress was 0.7, and again after application of 200 Newton loads, effective stress is 0.7 kPa. Why this is happening? Because we have already said that all the load is taken by the pore pressure and no load is transferred to the grain to grain contact. So that indicates sigma dash, that is effective stress, or the grain to grain contact, that values remain at the start and even after application of 200 Newton load. Now in a case once we allow the water to dissipate, or we allow volume change to happen, so that means pore pressure will dissipate slowly and delta U will eventually become 0. So that means U at that time will be 0.5, and if I want to calculate effective stress after we allow drainage, so that will be stress minus U. So total stress after application of 200 Newton load is 20.6 minus 0.5, that was U naught, so it will be equal to 20.1 kPa. So this is once load is transferred from the pore pressure to the grain to grain contact. Alright, so that was all for the first portion of the topic of the stress distribution that was due to the self weight of the soil. Now we will see that if we apply a vertical load, that means an external loading on the soil, that is like ground surface or anywhere in the field, so how to calculate the stress transformation or stress distribution through the soil medium. So there are two methods to estimate the value of the stress that is applied externally. First one is called as approximate method, and the second one is called as the method based on elastic theories. Now talking about the first method, that is approximate method. So in this method we assume that the load distribution happens with a slope of 2:1. To understand that, we see this figure here. Let me draw a more practical figure. So you see this is strip footing. We know that strip footing has a smaller b as compared to length, and this is the length of the strip footing, or this is the length. So generally if b is greater than let me correct that for you, smaller. If b is smaller than 10 times the length, then generally we classify that as a strip footing, but still there is not a hard and fixed rule. You can simply assume, in simple words, width is very small as compared to the length of the footing, and you can imagine all the walls footing that are provided for ordinary houses in Pakistan. Okay, so all of them are strip footings. So in a strip footing, this is an example. Remember that in a strip footing, when we consider the area, so we only multiply the area by multiplying the width with unit weight, multiplying width with the unit length. That means if I'm using meters as for calculation, for example, if b is 3 meter, so area will be 3 into 1 meters. Okay, because for in such cases we do calculation for per unit length. So this means for per foot, per meter, per foot, okay, in this way. So let me draw the cross-sectional view of a strip footing. So if this is a strip footing, we know that it is at a certain depth, and this is the foundation, and this is the, let's say, column, and a load P is being applied, okay. So if this is the width, so just at the contact point, so this here is the contact of the load to the ground surface. This is the ground surface, and we have dug up a hole, so this all is a ground surface, right? So this is the ground surface. So at this specific point here, I want to calculate effective stress. So that will be sigma naught is equal to P over A, and as we've already discussed, we multiply width with 1 to calculate the stresses for strip footing, because we go for per unit length, okay. So just under the footing, the stress is P over A, that is very high values. So according to approximate method, they say that load remains the same. This load P, it is fixed because this is the same constant value that is being applied. Only change occur in area. And how that change occurs? It says that the load spread increases, and by increasing the load spread, the intensity would reduce. And how intensity would reduce? We know that in the load intensity or the stress intensity is load per unit area, because this is constant. So if this value increases, so the value of sigma naught will decrease. That means the stress intensity will decrease. So same thing is happening here. The area of effect at a certain depth is calculated. Let's say this depth is, I am calculating stress at a depth of Z. So this says that the slope is 2:1. So we know this is width B is B because it is coming straight from top to bottom up to the foundation. Now it is spreading on the sides. So this is 2:1. So that means if I go a depth of Z, so this width will be 2 times Z over 2, half the time, I'm sorry. So this is Z by 2. So if we add the things up, so it will be B plus Z. So naturally, stress at depth Z will be P over B plus Z, and obviously 1 on that side. So now you see P is constant, but this value has increased. Previously it was only B, and now it is B plus Z. So that means intensity is reducing, and approximate method says this intensity is reducing by using this trapezoidal diagram, where we increase the area of effect by a ratio of 2:1. So in this figure, next figure here, we are assuming a rectangular footing. So it is more easier to understand. It has a length L and width is B. So there is load spread increase in width, and also there is load spread increase in length also. So this was the length L and this was the length B, and Z by 2 on both sides for length and width. So we have width equal to, at a depth of Z, the influence area will be Y width having a width of B plus Z and a length of L plus Z. So sigma Z at that point will be P over B plus Z over L plus Z. So it is very important to remember that in case of rectangular footing, there is an there is increase in the width and length, whereas in case of strip footing we only have increase in width, because we do not consider length in case of a strip footing. So this is how you will calculate the reduction in stresses with depth for any external load that is being applied on the soil. So now this was the approximate method. The second method that is based on the elastic theory has further methods, so we discuss them one by one. The first method that is based on elastic theory is called as the booziness method. So booziness method has certain assumptions. It says that soil is homogeneous material, soil is isotropic, and load is a point load, and it is applied on horizontal boundary. That means we only consider the ground surface, and we consider the vertical load being applied. We do not consider any inclined loading, okay, we do not do that, or we do not include any loading on an inclined surface, okay. They are not considered. Only considered is the vertical load applied on a horizontal boundary. And it says soil is weightless. That means that we consider the overburden stresses as 0. That means we will say based on booziness theory that stress will only transfer from top to the bottom for the external loading only. We are saying that soil is weightless, so we do not calculate any overburden stresses when we are dealing with booziness method or any other method based on the elastic theory, okay. So it says the soil is a semi-infinite medium. So we have already seen in previous examples that we draw soil layers, and then we say, okay, this is the load being applied, okay, and we know this is the width, and we multiply the values. So we know the dimensions. So this is finite values. But you see, on lateral dimensions we do not tell that okay, this much is the boundary, so it is infinite in the horizontal direction. So such diagram where we have lengths in one direction, they are calculatable and that is finite. So and the other side is having no ending boundaries, so that is called as a semi-infinite medium. And in soil examples we say that we know the depths, we know the dimensions from top to bottom in vertical direction, but we do not know how far they are extending laterally. So such an example is called as the semi-infinite medium. So let's talk about the first method, that is the booziness method. So the equation for the booziness is this one here. So if you look at the diagram on the right, so if we have a load applied Q, that is a point load applied on a horizontal surface, so this red color is indicating the line of action of the point load, okay, and I'm interested to find load at this point, the cross that I just drew. I want to know the sigma z value, and this is due to the load Q, point load Q, that is being applied on the surface. So R is the radial distance from point of action to the point of interest. This is cross is the point of interest, and line of action is Q on the line on which Q load is being applied, and Z is the depth of the point of interest from the ground surface. So now we understand that Z is the depth and R is the radial distance from the point of application of the Q. So we come to the equation that says sigma Z is equal to Q over Z square 3 over 2 pi 1 plus R square over Z square raised to power 5 by 2. R or Z we are already familiar. Q is a point load being applied, so that can be summarized to Q over Z square into KB, where KB is the coefficient of booziness, coefficient of stress. So this was the booziness method. Later on, this was actually only for point load. Later on, other scientists modified that for a line load also. So for line load we use this equation, that 2Q over pi Z cube over X4, where X is the diagonal distance from the point of action of the load to the point of interest. So this is the X value, and we can calculate Z and R at previous, just like the previous example, depth and radial distance from the point of interest to the point of application of the load. So X is equal to R square over Z square. You can see that it's a right angle triangle. So from this equation you can tell that X value can be found from here. Okay. The second method is Westergard's method. So the assumption of Westergard is that it says that soil is made up of very rigid layers that only bend in vertical direction and there is no lateral movement. So that means it's considering soil to be in layers, that is more close to real life, and we apply load Q. So it says there will be deformation only happening in the vertical direction and there is no lateral movement. Okay, there is no lateral dimension. So this is the assumption of Westergard method, and the equation is Q over pi Z square 1 plus 2R over Z square 3 by 2, and that is already same just like the previous example, that this is load applied Q and this is the ground surface and this is the point of interest. So Z is the depth of the point of interest and R is the radial distance from point of action or the line of action of the force to the point of interest. Okay, and you can summarize that to the Kw, where is the Westergaard's coefficient of stress, Kw is. You can also use this equation for Westergard. This includes a parameter A that is based on the Poisson ratio of the soil, so it is your choice whatever method or whatever formula you want to adopt, and also depends on the amount of information that you have. So a little comparison between the two methods, Westergard and the booziness method. Okay, so the chart has been plotted between R over Z and then Ki means it can be either Kw or Kb. So you see there, if the R over Z value is larger than 1.5, then Kb and Kw do not have any difference, they will give you the same value of stress. Whereas for R over Z less than 1, Kw or the Westergaard's coefficient for stress gives us more conservative value of stress as compared to the booziness value. Okay, so more or less real life geotechnical engineers prefer Westergard method because more or less we have sedimentary soils and sedimentary soils is made up of layers, so that's why they prefer the method. Okay, alright, so then we talk about the stress distribution diagram. So we have so far seen that we can only do this calculation for point loads and they are very reserved that they have to be applied to horizontal surface, but generally in our daily lives we have to deal with footings Okay, we can have a strip footing, we can have a rectangular footing, we can have a circular footing. So in all those cases, how to calculate the stress? Okay, so the equations of Westergard and booziness both were modified by later researchers, and they came up with the ideas of calculating the values. So for example, this first graph here, okay, so this graph here, this will help us to find out the effective stress due to the loaded area. Okay, we call that as a UDL, or a uniformly distributed load. Let's call it as a uniformly distributed load. So it says that if I draw a cross section, so if this is the length, so it says that it is applying throughout the area. Okay, it is not a point load, it is a UDL. I'm sure you might have studied that before in your mechanics classes, but for jogging your memories, so this is the UDL that is being applied uniformly on the loaded area. Okay, so in the figure here, so y is the length and x is the width of the loaded area. If I draw it here in a more easier way, so it says that this is y and this is x, and this is the loaded area, or you can say that this is the footing that you have in your building. Okay, so if you are interested to find the stress due to this footing at a certain depth z, then we can use this formula that is provided in the figure. So it says there are two terms explained here, one is m and one is n. So m says it is equal to x over z, and n says it is equal to y over z. Now they are interchangeable. You can also say that this is y over z, and you can also say that this is x over z. You will get the same values, but either one of these side has to be divided by z to find m, and either one of the values has to be divided by z to find out the n value. So they are interchangeable. You can make m and n interchangeable. So you will get the value of m and n, and z is the depth of interest. So you see here that you want to find out stress, and this is very important to note here that this method will only tell you the stress at any 4 columns. According to the graph, they say that the stress value at any of the corner is same. It will be same here, it will be same here, it will be same here, and it will be same here. But you cannot find the value at any other point. This method will only tell you the stresses value at the corner of the uniformly loaded area. Okay, it can be a square, it can be a rectangle, but it has to be either of them. But it says that it has the constant value at all the 4 corners. So if we are if I draw it in a diagonal position, just like the one has been drawn in the figure here, so this was the area, this is x, this is y, and I am interested to find the stress at a depth of z meters or a foot. So I will use the formula here. It says sigma z is equal to q naught into y. So q naught is the UDL value. It will be pound per foot square, or maybe kilonewton per meter square. Okay, because it is UDL, so its units has to be in squares. Okay, so q naught value will be provided to you in numericals. So that is the amount of UDL being applied, and you multiply this with I, that is the influence factor, and it will give you the sigma z, that is the stress acting due to this loaded area at a depth of z at any of the 4 corners of the loaded area. So you see here, so in the figure, on x-axis we have value of n, and on y-axis we have value of I, and m values are used by different graphs here. So let's understand this with an example. So let me do an example. So let's say I have a loaded area. So let me wrap this up for now. So if I have a loaded area, and let's say x is equal to 5 and y is equal to 10. So I want to calculate m and n. So let's say I say 10 by, and I am interested to find at a depth of, let's say, 10 meters. So z is 10, so 10 by 10 gives me 1, and n was 5 over 10, so this becomes 0.5. So how did I get the values of 10 and 5? So I use this as y and use this as x. Okay, so now what will I do? I'll go to the chart and look for the value of 1 and 0.5. So first I'll look for 0.5. So this is the 0.5 value, because this is the chart that is for the n. On x-axis we have n, and I have to look for m is equal to 1. So let's say, so this is the chart for m is equal to 1, sorry, m is equal to 1. So let me follow that chart for you. So I'll highlighting this with the red color here. So you see it is moving down there, and the n was 0.5, so I move up, so moving up, so they are interfering at this point. So then I move left from here. So this is the value of I. So let's say I choose the value of, let's say I is 0.1, 0.1111, this should be 0.11, so let's say 0.118 is the I value from the chart. Okay, because it is less than 0.12, so that's why it chose a value of 0.118. So how can I find stress at a depth of z? So sigma z will be equal to q into I value. So let's say if q was 100 kilonewton per meter square, so at a depth of 10 meters it will be equal to 100 into 0.118. So this will give me the value of stress set at a depth of 10 meters by using this chart. Okay, so this is the similar philosophy that applies to all the similar charts. So the next chart here, this is for the circular footing here. So you see here the formula is little different, but the idea is same. The UDL is explained by the value q naught. Okay, and because the circular footing, so half of the diameter is called as radius, so that has been indicated as r. And if you are interested at a depth of z, okay, and you want to find out the area at a distance of x from the center of the loaded area, for example, if you are interested finding the stress here, and this distance is, let's say, x, okay, and the depth of the distance is z, that is indicated by here. So you can use this formula, that is I into q naught over 100. I will come from the chart, and q naught is the UDL value that is being applied. So let's see where do we get the values on x and y axis. So on y axis we have z over r, that is the z is the depth of interest, that is from the ground surface, that where we are interested to find out the stresses, and r is the radius of the footing. So z over r will come here, and the lines, they are x over r. You see all the lines, they are based on x over r. X is the point of interest where we are wanting to find out the stress, okay, and r is the radius of the footing. So wherever the two values join, for example, if we have a z of z over r of 6 and x over r of 4, so let's say z over r is 6, so I'll move here and I look for the value of 4, x over r of 4. So they are interfering at this point. Okay, so this point, so I'll move straight up. So this is the I value. So this is 1, this is 0.5, so that means this value is, let's say, 0.7 is the I value here. So I will put the I value here, 0.7 multiplied with the Q, that is load being applied over 100. So it will give me the stress at a depth of Z and a distance of R from the center of the footing. Then lastly, the last chart, that is also very similar but a little different. This is for embankment loading. So you see in an embankment, general embankment figure looks like this. Sorry, it looks like this. Okay, so we can imagine the load. So the first section is trapezoidal, this section is trapezoidal, and the remaining section is rectangular, and then again we have trapezoidal section. So in this figure it has shown us half of the embankment loading. So the trapezoidal section has a length of A, and the horizontal loading has a length of B. Q naught is the top of the maximum value of the Q naught that is being applied at the center of the embankment. Z is the depth of interest, and sigma Z is the point of interest. Okay, so formula is I into Q naught. So on x-axis we have A over Z, and on the lines are B over Z. So we will look for the values where they intersect, so they will tell us the I value that is on the y-axis on the left side. Okay, so all of these are simple methods. So if you have we can discuss in our live classes if you have still any confusion, so we can sort that out. Okay. Alright, so this was for using of the figures. Then the next method that is also based on elastic theory is called as Newmark's influence charts. So you see here, Newmark was a person, he got a solution for irregular shape footing. So you see here in previous examples, the first one, booziness and Westergard, we can only do for point loads. Then came this first diagram here, this is for rectangular or square footings. Then we have circular footing here, and then lastly we have this embankment loading here. But we know that in real life there are many different shapes. Sometimes if we have a combined footing, so we have to give maybe a tapered shape here like this or like this. Okay, if we are giving the load at a corner, then a strip footing can be like this. Okay, there can column here, column here, column here, column here. So there are a lot of variations in real life, so these methods don't apply easily to such examples where there is some irregular shape footings. Okay, so Newmark came up with a formula or a method to that will work out for irregular shape footings. So what did he do? He made charts like this. You see, these are some spiral circles. Okay, so each chart has an influence value that just like one here, c is equal to 0.005. okay. So different charts are provided, so we can use this chart to find out the stress value. Let's do another example. This is a same chart, so we have cut out the portion so that is more easy to understand here in the example. So you see here there is a scale on the x-axis on every chart. So this is O to Q. So let's say if this is if we have a footing and we are interested to find out the stresses at a depth Z. Okay, so what will I do? Let's say if this is 10 meters, so I will use the scale equal to depth. That means this is Z. So that means this is 1 2 3 4 5 6 7 8 9 and 10. So that means according to this scale, this is 10 meters now. Okay, conversely, if this was, let's say I was interested to find out at the depth of 20 meters, so what will I do? I will make this scale from 0 to 20 as 20. So this will be 0 and this will be 20. That means this will be 5, this will be 2 4 8 sorry 2 4 6 8 12 14 16 and 18 and then 20. So you understand that the scale here on x-axis is dependent on the depth of the interest, where you are interested to find out the stresses. Now what do we use with this scale? So we will use this scale to plot the figure of the foundation or figure of the footing. So that means so let me convert that for you. So that means here if you look, so this is almost the same scale. Okay, so from 1 2 3 4 so and 5 1 2 3 4, so 4 digits here and 8 digits here are equal to 20. So I will use this figure to plot the values here. So that means I have drawn the figure here. So this was 1, let's see, 1 why is it not plotting? 1 2 3 4 5 6 7 8 9 10 11 12 and 13. So that means this side is 26 meters. Okay, so similarly, using the same scale, I'll plot the figure here and I'll use this to plot the length also and the remaining lengths. Okay, so once we are done with this plotting, so what will I do? I will take this figure up. Let's see, just a minute. I select the whole figure and I will place it on top of the diagram here. Okay, so now now it is very simple. I only have to calculate the number of boxes that are coming within this. So let's say this is 2 3 4 5 and maybe this is 10, 18, 20. So these are all boxes you have to count. Okay, so this box is almost half, so I count this as 0.5. This is almost 0.25, so it's approximation really. This is very small, so maybe 0.8. This is 0.1. So you have to add all the boxes. Okay, so that means I have to add all the boxes that are coming within the figures. And once again, just to repeat, I plotted this figure based on the scale that I achieved from the scale shown on the bottom of this figure of this chart here. Okay, and that chart has a length of 0 to 10, that has shadow 0 to z, that is point of interest. Okay, so we calculate all the boxes that are coming within, just a minute. Okay, this means all the boxes that are coming inside this area. So at the end, to find out the stress value, so stress will be equal to simply I, that is the influence value that is mentioned on the chart, I from here multiply by number of boxes. Okay, so this will be the stress value at a depth z for an irregular shaped foundation. So you can choose any shape and then you can later on plot it. Okay, so this was the Newmark's method for plotting of the stresses for irregular shaped footings. Then we have some few last topic for this chapter. They are very, very important. So this is called as pressure bulb. Okay, so pressure bulb is a stress isobar, that is a line connecting all the points of equal stresses. So isobar means, iso means single or one, and bar is mean for pressures. So a line that is having a single value of pressure, okay, that is called as a pressure bulb. So if I apply a vertical load and if I connect all the points that are having same value of stresses, so if I join them, so that is called as a pressure bulb, because that joining is going to happen in form of a circle. Okay, before I explain you pressure bulb, let's go to the thing that let's say this one here. Okay, first I'll talk about this, that is vertical stress distribution on a horizontal surface. So that means a load is applied on, this is the ground surface and I'm applying a load Q. This is the line of action. Let me change the color. So this is the line of action. So I want to see at a depth of z how this load is influence is transferring from the sides on the radial distances. So if you remember, sigma z is equal to Q over z square into K value. It can be K Westergard, or it can be K of the booziness, whatever method you want to adopt. Okay, it can be KW, KB. Okay, so if we put in the values, so what will I do in the equation? Okay, let me write that equation. I might be wrong, but you can correct it later on. This was 1 plus r over z square raised to power 3 by 2. This was equal to kb. If I'm using booziness equation, I might be wrong, but you can check it. Okay, so you see here what we are going to do is that because we are at a fixed depth of z, so this value will remain same, z will remain same. Okay, and this will remain same. So what will I do? I will choose value of r equal to 1, r equal to 2, r equal to 3, r equal to 4, and I will find out consecutive value of sigma z. Okay, z is same, only r is changing from 1 up to maybe up to a certain value. So if you plot those values, so you will see here it will form plot in a bell shape like this. So z is constant and only r is changing in the equation here. Okay, z is constant, only r is changing. Now a similar figure is drawn. Now we see vertical stress distribution of vertical plane. Okay, so same, this load is applied Q on a vertical stress. This is the application of Q. Okay, So now what we are doing, r is fixed. In this case, r is fixed equal to 0, and here let's say r is equal to fixed 2 meters. For example, it can be 4, whatever value you want to do up. So we fix our value of r, and then what we do, we change the value of z. Z is equal to 0, 1, 2, 3, 4. We go on, and we find out the values by plugging in this equation. You can either use booziness, or either you want to use the Westergard, whatever you are comfortable with. So you can use that equation. Okay. So we will get a distribution like this. This was for horizontal distribution, and this was the vertical distribution. Okay. So if we join, you can check that with Excel. Okay, you can use Excel, and then you can find out once you merge these two diagrams. Okay, for example, let me I might be wrong in my plotting. So if this is z, so it is distributing like this. So here it is distributing like this. Okay. This is merged. I have merged the stress distribution horizontal planes and on vertical plane. So once you join these two figures, so it will be plotted in this form. That is called as a pressure bulb. Okay. So, and at this point, at any point on the bulb, the value of stress or sigma naught will be constant. Okay. And interestingly, you can plot as many pressure bulbs as you want. Okay. For example, this is Q. So you want to find out the pressure bulb of different densities. For example, I can plot the pressure bulb. Let's say for this one is for, this is the line of action. This is the pressure bulb for 0.9 sigma naught. Okay, this is pressure bulb for maybe 5 sigma naught. Okay, then maybe we can draw another pressure bulb. That pressure bulb is, let's say, for 0.7 sigma naught. Okay, so this is how we can plot stress intensities. Okay, maybe I can draw a bigger one. Sorry, let's say of 0.9 sigma naught. Sorry, 0.2. Because as we go bigger, the intensity would go on reducing. Okay, so this is how you can plot the pressure bulb by simply plugging in the values of R and Z. Okay, and you can do that pressure bulb for as many intensities you want. Then we have a definition that is called a seat of settlement or active zone. So according to Terzaghi, vertical stress is considered of negligible magnitude when it reaches 20% of the applied vertical pressure. Okay, so this means, or we can say that if this is the stress on the top, so on a pressure bulb of 0.2 sigma naught or 0.2 Q, okay, where the intensity is reduced by 80%. You see, it is 80% lesser than the applied value. That is 0.2. If this was 100, so that means it is 20. So a stress intensity 20. The Terzaghi says that this is all of the important settlement will happen within this zone. So this is called as the seat of settlement, or this is called as active zone. So a pressure value where it reduces to 0.2. So here its value will be reduced to 0.2, and we know that on a pressure bulb everywhere it will be 0.2 Q. So definitely, so this circle, this is called as where the intensity is 0.2 isobar. So that is called as the seat of settlement. Okay, so the region within 0.2 isobar is known as the seat of settlement or active zone. We have already discussed that. Okay, so then we have critical depth. So critical depth, the depth within which soil compression contributes significantly to the surface settlement, is called as critical depth, and it extends to the point where applied stresses decreases to 10% of the effective urban stresses. This is for fine grained soils, and for coarse grained soils the critical depth extends to the point where applied stresses decrease to 20% of the effective overburden stresses, where it is 10%, and for coarse grain it is 20%. Okay, this is critical depth. And lastly, for elastic isotropic semi-infinite soils, the active zone okay, or the critical depth or the active zone, the C2 settlement is up to 1.5 B. Okay, if B is the width of the footing, so if we go 1.5 B, so that will be the point where the stress is equal to 0.2 Q. So this is important to remember, that the seat of settlement, that is up to 0.2 intensity of the applied stress, it is at a depth of 1.5 B. And a different thing is critical depth, okay, that is 10% of effective overburden stress for fine grained soils and 20% for effective overburden stresses for the coarse grained soils. So this pretty much covers up the stress distribution for your geotechnical engineering 2. If you have any questions, so we can discuss in our live classes. Thank you very much.